All right, so welcome everyone to this week's edition of GROOT. So today we'll be hearing from Baylee Schutte on the projective span of wall manifolds.
Thanks so much for the introduction. I'm really happy to be back at GROOT. I think last summer I gave a talk and it was really great because I met Nikola Sadovec and Jihan Baron from that talk, who are now my collaborators. So it was very fruitful. So I'm hoping I can meet more of you and maybe we can do cool math together. But I should just sort of say, I'm going to tell you mostly about the projective span of wall manifolds. This is a new paper that is completely joint with my supervisor, Mark Grant. And then I'll tell you a bit about some other projects I have with Nikola and Jihan as well, but it's separate from the wall manifolds stuff. Okay, so before I tell you about projective span, I want to tell you about span, which is the more classical thing, otherwise known as the vector field problem. If you have a smooth manifold, a vector field on this manifold is a smooth section of the tangent bundle. And we say that K vector fields on M are linearly independent if they're pointwise linearly independent. The span of M is defined to be the maximal number of linearly independent vector fields. So I'll kind of use this fact a lot that if you have a manifold with span at least K, so it has K linearly independent vector fields at least, then you know that the tangent bundle admits a rank K trivial subbundle. And this is my notation here, this R underline for a trivial bundle, but I'm kind of implicitly assuming I'm working with real manifolds here, but it doesn't have to be real manifolds. It's just my notation. The vector field problem has a really rich history. I could tell you a lot of stuff about span, but probably the most famous span calculation is the span of spheres. Probably most of us have heard of this, and I just wanted to mention it. It's really relevant actually to my problem. Hurwitz and Radon independently calculated a lower bound for the span of spheres in like the 1930s or something, very, very long ago. They were actually algebraists studying certain kinds of composition formulas for like associated to some quadratic forms. And somehow this was related to vector fields on spheres, but the methods that they used were really, really elementary. Nowadays, this Hurwitz-Radon lower bound is calculated in textbooks in a really slick way using Clifford algebras and stuff. But this isn't how they did it. And decades later, Adams finished the calculation of the span of spheres. He found that the lower bound Radon and Hurwitz had calculated is the same as the upper bound. And to do this, he used famously K-theory and, of course, Adams operations. But the answer is in terms of these Radon-Hurwitz numbers. And it's not really important what they are, but they'll kind of come up later. So I just wanted to write this. There's another cool example that I'm trying to kind of popularize because people don't really seem to know this about the Stiefel manifold. So VNK is the Stiefel manifold of K frames in Rn. And if K is equal to 1, Vn1 is the n-1 dimensional sphere. So the span of that is complicated and we've already seen the answer. But if K is bigger than 1, then the Stiefel manifold, it turns out, is actually parallelizable. So the tangent bundle of the Stiefel manifold is totally trivial. This is kind of... Yeah.
Just for someone who don't do manifolds, can you say just a word what the Stiefel manifold is? Or should I just think of K-frames and Rn in a manifold setting?
Yeah. So like a point in the Stiefel manifold is like a tuple of vectors in Rn, which are like orthogonal.
Okay, great.
Yeah,
so what one would expect, kind of, to some degree.
Yeah, maybe, I guess maybe there's an easier, one way you can think of them is as a homogeneous space. So you can view it as ON mod ON minus K, for example. So you could think of it as a homogeneous space as well. Anyway, I don't know if that helps.
It does. Thank you.
Okay. Well, yeah, these Stiefel manifolds cause the homotopy groups of them cause a lot of problems in algebraic topology. So I think it's kind of interesting that something about them is simple. But I also need to tell you for later what the stable span is. I'm not going to go into this too much, but there's a particular stable span calculation that's really critical for me. So I just kind of want to get this out at the beginning. We have a smooth manifold. This stable span is defined like this. I know this is, well, I don't like this notation, but this is the notation that exists. So the stable span, the way that you calculate this, you take the tangent bundle and you add on a rank R trivial bundle. And you choose this R so that you maximize this number, the span of this, the tangent bundle plus this trivial bundle. And then once you've maximized that span number, you subtract off whatever the R was. And this is the stable span. So hopefully, if you can see from this formula, maybe I'm going a bit too quickly, but this stable span is bounded below by the span of the manifold, and it's bounded above by the dimension of the manifold, or equivalently, the rank of the tangent bundle. So maybe just for a simple example, it's well known that spheres are stably parallelizable. So if you take any sphere and you add on a trivial bundle to the tangent bundle of that sphere, it will be completely trivial. It will rearrange things, and the stabilized tangent bundle of any sphere is totally trivial. So the stable span of any sphere is equal to the dimension of the sphere. And for even spheres have non-zero Euler characteristics, so they don't admit any non-vanishing vector fields. So the span of an even sphere is 0, but the stable span is still the dimension of the sphere. So stable span and span can be meaningfully different. Now, the important example that we have to try and remember for later is the stable span of complex projective space. So a French mathematician, Stier, calculated in 1967 this. So the stable span of CPN ends up being 2 nu n plus 1. Nu n plus 1 is the two-adic valuation of n plus 1. So nu n plus 1 is the biggest number such that 2 to that number divides n plus 1. It's not really important. It's just interesting. And this is intimately related with those Radon-Hurwitz numbers showing up in the span of spheres. So this is a cool calculation. It uses Clifford modules to get at the lower bound, and then Stier uses complex K theory to get at the upper bound and determine this calculation. But also the arguments he uses can give you the stable span of real and quaternionic projective spaces as well. I just wanted to mention. And merely for the purposes of illustration, I've just made you this table so you can kind of see. So n plus 1 is in this row here. And you'll notice that n plus 1 is only ever even. And that's because if n plus 1 is odd, then nu n plus 1 is 0. So I've just removed the zeros from this table is all that's happened here. And you can kind of just see what's happening with the stable span of CPN. It doesn't grow very much. It's very stable in a way. And I looked at like the first 3,000 n plus 1s, and 20 is like the biggest that it gets really in that period of time. So it doesn't grow too much. Okay. What I've told you so far is about span, and I've given you a few examples, and I've told you about stable span, particularly about the stable span of CPN. I'm not really that interested in vector fields. I'm more interested in line fields. So a line field on a manifold is now a smooth section of the projectivized tangent bundle. So the fiber is real projective space. And this time, if we have k line fields, we say that they're linearly independent. If for each point on the manifold, the k lines assigned to that point, they span a k-dimensional linear subspace of the tangent space at that point, is what I mean by that. And mutatis mutandis, projective span is defined to be the maximum number of linearly independent line fields on the manifold. So line fields instead of vector fields. And in a similar way as before, you have k linearly independent line fields on your manifold if and only if there are k line bundles which split off the tangent bundle of the manifold. So this is a kind of yoga that I will keep using a lot. Now, we don't have a lot of manifolds whose projective span we know, but here's a nice simple example. If you have the Klein bottle, the tangent bundle of the Klein bottle will split into one trivial line bundle and two non-trivial ones. Well, sorry, one trivial line bundle and one non-trivial one. So the span is 1 and the projective span is 2. If you think of the Klein bottle as a circle bundle over a circle, you can realize the Klein bottle as an instance of something called a solve manifold. I don't really know a lot about these solve manifolds, but I mean, what they are is a homogeneous space of a connected solvable Lie group. But I've come to learn that they are important in the study of dynamical systems. And they also apparently arise naturally in the theory of discrete subgroups of Lie groups. So I think the point is there's some kind of geometry, algebra, number theory thing going on with these solve manifolds. And there's this really striking annals paper by Auslander and Sharba, where they show that every compact solve manifold is line element parallelizable. And by that, I mean the tangent bundle of any compact solve manifold splits completely into lines. So the projective span is equal to the dimension of the solve manifold. This was, I think, a very important result. And there's another cool example I wanted to bring up. You have this projective Stiefel manifold. So we have this Stiefel manifold from before. And this time you quotient out by this Z2 action where you identify a frame with its negative. And you get this projective Stiefel manifold thing. And it's known that this thing is stably line element parallelizable. So if you take the tangent bundle of the projective Stiefel manifold, you add on some number of trivial line bundles, the whole thing will split completely into lines. And I have some dubious circumstantial evidence in the form of computer experiments that this thing is actually line element parallelizable. You don't need to stabilize. But I don't know how to prove that. I just think it might be true. The thing with this projective Stiefel manifold, knowing its span and its projective span has implications in immersions of real projective space, and also in the classification of bundles over RPN. So there's reasons that people want to know the span and p-span of this projective Stiefel manifold. And really what I'm trying to get at with this very short list of examples is there's some cool manifolds lying around with different uses in different areas, and sometimes it's really helpful to know about vector fields and line fields on them. So hopefully this convinces you a little bit of that. This is the last part of like the general, just showing you about p-span and span and stuff. I thought we should just do some quick, easy properties about p-span so you can get to know this interesting invariant a little bit better. One quick thing, if you have an n-dimensional manifold, projective span of that manifold can't be n-1. And just as a quick sketch argument, just assume for a contradiction that p-span of an n-dimensional manifold is equal to n-1. Then the tangent bundle would split off n-1 line bundles. but it's a rank n bundle, so you would have precisely a line bundle amount of information left over. So pspan is then just n, which is a contradiction to what we assumed. So you can't have n minus 1 pspan. Another obvious thing, or easy thing to see, is that projective span is always at least the span. So if you have span k, say, that means the tangent bundle has a rank k trivial subbundle. You can think of that rank k trivial subbundle as the direct sum of trivial line bundles. And all of those trivial line bundles count towards the projective span. Right, but the point is this leftover rank n minus k bundle could split off more line bundles. So projective span could be more than span. Also, this is a useful fact. If you have a simply connected manifold, then there's no difference between the span and the projective span. And the reason for this is if you're simply connected, you only have trivial line bundles. Maybe I shouldn't explain more than that, but if you're simply connected, you can only have trivial line bundles over M. So the span is the same as the pspan. And this is quite useful, for example, with spheres. So we know the span of spheres. That's a really non-trivial computation. But since spheres are simply connected, we immediately know the projective span. Final thing I wanted to mention is if you have a covering of smooth manifolds, then projective span of the cover is at least projective span of the base. So you can imagine, like, you have this base manifold, you have some vector fields or line fields on it, and there's some way to lift those to the cover. And the cover might have more vector fields or line fields, but maybe it's somewhat believable that this could be true. So for example, if you wanted to compute the projective span of RPN, you could notice RPN is doubly covered by the sphere. We already know the span and pspan of spheres. So we have immediately that pspan of RPN is bounded above by pspan of spheres. And with some extra work, you can see that equality actually holds here. Okay, so that's the crash course in span and pspan. So I want to tell you now what wall manifolds are, because we computed the projective span of wall manifolds. They're really, really fun manifolds. I wish I could talk about them a bit more. But to construct them, I first have to tell you what a Dold manifold is. So m and n are integers bigger than or equal to 0. The Dold manifold is this here. So we have an m-dimensional sphere product with CPN, and we're quotienting out by the antipodal action on the sphere and complex conjugation on the CPN part. So that's what this Dold manifold is. And Dold used the odd dimensional ones as generators of the unoriented cobordism ring. So they're really interesting guys. If you reflect in the last coordinate of the sphere, that's going to commute with this antipodal action. So it induces a homeomorphism of the Dold manifold, PMN. And you build the wall manifold by taking the mapping torus of the Dold manifold with respect to this reflection. So the wall manifold QMN is the mapping torus of PMN with respect to this homeomorphism here. So you take PMN, you cross with the interval, you have this like cylinder, and you glue the ends of the cylinder along this reflection. So you get some crazy thing. And Wall used these classically to get at the two torsion part of the oriented cobordism ring. They're just a really geometrically interesting manifold. And we found that the projective span of these wall manifolds satisfies this formula. So maybe you recognize this 2 nu n+1 thing from earlier. But the projective span of the wall manifold QMN is 2 nu n+1 plus m+1, where this nu n+1 thing is the two-adic valuation of n+1. One good thing about this is that we now know that span and pspan can be arbitrarily different. And we really didn't know that before. mostly every example we knew the span and pspan only differed by 1. So it's really good to know if m and n are both even, it turns out that there's only one vector field on the wall manifold QMN. But our result says you can split off m non-trivial line bundles in addition to that single trivial bundle. And one other thing I just wanted to mention, we thought this was kind of surprising because the span of the Dold and wall manifolds is a complete mess. I mean, it's really, really rough situation. People do not know much about vector fields on these manifolds. So we were just really surprised that we got such a compact and simple formula for the projective span. Now, I'm not going to go into like the details of the proof or anything, but the proof is actually very, very simple. It's really constructive. And I just want to give you an idea as to how we did it. And unfortunately, I have to tell you something about Clifford algebras for a second. I'm not an expert in Clifford algebras, so probably other people know more about them than me. So if you're annoyed by what I say about them, I'm sorry about this. But k is some integer bigger than or equal to 0. I'm going to let ck be my notation for a free associative algebra over the reals with k generators. And these generators have to satisfy 2 relations. Each generator has to square to -1, and ei times ej has to be equal to minus ej times ei. There's a lot of stuff packed into here, but let's just not focus too much on the details. C0, you can see, is just the reals. And C1, you can identify that with the complex numbers, for example. And C2 is non-canonically isomorphic to the quaternions. So I've written down an example map here. You could send the first generator to I, the second generator to J, and then you can send E1 times E2 to K, for example. But there's, other possible ways of doing it. Now, the thing with the Clifford relations, if you give yourself a monomial in the generators of this Clifford algebra, if you kind of think about it for a minute, you can see that you can reorder, because of the Clifford relations, the elements in this monomial so that they're occurring with indexing that's strictly increasing. Because I can flip around any EI and EJ that are multiplied by each other, and then I just get a sign. You just pick up signs as you kind of swap them around. So you can always reorder them so that the indexing is increasing. And if you collect together all these monomials with indexing like this, you get an additive basis for the Clifford algebra. And if you put a plus or minus sign in front of these monomials, you actually get a multiplicative subgroup. And I'm going to call that GK. And for a couple of slides, we have to remember this GK. So this GK is all the monomials in the generators of the Clifford algebra where the indexing is strictly increasing. And there's plus or minus. Now give yourself an inner product space that has a CK module structure. So there's some kind of Clifford algebra action on this. I'm calling the module map rho. And I'm going to write AI for the automorphism of the vector space coming from the ith generator of the Clifford algebra under this module map. This gives rise to something called the Clifford multiplication. So you can act on a vector in the vector space by a generator of the Clifford algebra using this automorphism. And then you can build using this averaging process. It's not really, I don't want to get bogged down in the details, but you can build yourself an inner product, which is GK invariant. So this is this multiplicative subgroup. So we can build a new and a better inner product on this vector space that's GK invariant. And the point of this is that if you take this sphere on V, with respect to this GK invariant inner product, then the Clifford multiplication will stay on the sphere. So what I'm trying to convince you here is that these Clifford algebras and the Clifford modules associated to them, they're just the perfect thing for building vector fields on spheres. So what we have here, this V, it's an inner product space. We've built a GK invariant inner product on it. We're looking at the sphere on this thing, and there's an action of this Clifford algebra. Look at a point on this sphere. This set is an orthogonal K-frame. So here we have the Clifford multiplication. And I just want to kind of run through this argument a little bit so you can see how it works. So the first thing we want to check is that this point X on the sphere is orthogonal. It's tangent, or EI times X is tangent to X on this sphere. So we want to look at the inner product of X with EI times X. And since this inner product is GK invariant, I can multiply both arguments by EI. So that's what I've done here. But we know by the Clifford relations that EI squares to -1. And since it's an inner product, I can pull out this -1. And the inner product is symmetric, so I can swap the arguments. And so we get this here. So we see that the inner product of X with EI times X is equal to minus itself. So it must be 0. So that's showing me that EI times X is always tangent to X on this sphere. And the other thing we need to check is that the elements of this set are pairwise orthogonal. But you can hopefully see you just play the same game. So this time you'll multiply everything by like EI times, or EJ times EI, or some combination of this, and then you just use the Clifford relations, and you'll have the same kind of game. Okay, so sorry about the end of aside about Clifford algebras. They will come back in a second. I can nearly tell you how we got a lower bound for the projective span of the wall manifolds. The big key idea is really these quasi-invariant vector fields. So this is the last thing I have to tell you about. So now we have a manifold with a smooth G action. And now we call a vector field on M quasi-invariant or G quasi-invariant if for every group element, this diagram here commutes up to sign. So what I mean is we look at this diagram, we can take a point on the manifold, we can apply this G action and get a new point on the manifold. Then we can apply a vector field and get some tangent vector. Or we can go around the other way. So we can take this point, we can get a tangent vector by applying the vector field, and then we can apply the differential of the group action to get a new tangent vector. And I'm not saying that this diagram has to commute on the nose. I'm saying that the tangent vectors you get at the end, they can either be pointing in the same direction or they can be pointing in opposite directions. Either or. And the upshot of this is that if you have a finite group acting freely on the manifold M, then when you look at the quotient M mod G, the tangent bundle of that quotient can be described as a quotient bundle. And this means that you can look for quasi-invariant vector fields on M. And when you quotient out by G, those things will become line fields on the quotient. So it's a bit of a long definition, and I think it's just easiest if we just do a simple example. Hopefully, let me know if you want to go back or see anything else. Hopefully this will make things a little bit clearer. I wrote this talk for a conference that I was at in the Isle of Skye a couple of weeks ago, and I didn't really have like all of the technology things that I usually have. So I made this picture in Microsoft Paint, and it's just, I'm sorry, it doesn't look very nice, but I think it will do the job. So what we have here is, okay, Rho is a reflection in one coordinate of a circle. It doesn't matter which coordinate. And I want to view the Klein bottle as the mapping torus of the circle with respect to this reflection. And I want to try and show you that on the cylinder before we do the gluing. So we have the circle across the interval. We got this nice cylinder. There's a quasi-invariant vector field on this cylinder. And when we do the gluing to build the Klein bottle, this quasi-invariant vector field will become a line field on the Klein bottle. That's what I want to convince you of. So we have just the cylinder, S1 cross the interval. And if you see these orange vertical lines, that's a vector field on the cylinder, and it's going to descend to a perfectly good vector field on the Klein bottle. There's no problem with that when we glue. It's going to be fine. The problem is this blue one. So I'll try and describe the problem. So if you look at the blue vector field here, now look at the top boundary circle of the cylinder. Just to make things easy, let's say we're going to reflect in this gray line. So this row is describing reflection in the circle in that gray line. And let's look at a point on that axis of reflection. So this point here on this gray line, when we apply rho, it's not going to move. It's fixed because it's on the axis of reflection. Now let's say the blue vector field has assigned to this point a tangent vector pointing to the right. When we differentiate the reflection, that's going to flip the tangent vector to point in the opposite direction. And that is going to cause problems when we glue to build the Klein bottle. So this blue thing is not going to descend to a well-defined vector field when we glue, because we'll have a point which has assigned to it two tangent vectors that are different. So it's not a well-defined line field, but since the vectors are in the same line, it's going to be a perfectly good line field. So this quasi-invariant vector field, this blue thing, it will become a line field on the Klein bottle. I hope this is roughly convincing. Okay, so this is how we did the lower bound. I can put all the stuff together, the Clifford algebras and the quasi-invariant things. So we're looking at these wall manifolds. We're trying to find line fields on them. First thing we notice is we can write the wall manifold as this iterated balanced product. So this is the Dold manifold part, and this is the mapping torus part. It doesn't really matter the details, but these two involutions, these Z2 actions, they commute with each other. So you can actually write the wall manifold as this product space modulo a free Z2 cross Z2 action. So this is very good. And I mean, the vague idea of what we do is we just look for quasi-invariant vector fields on this product space. And these quasi-invariant vector fields have the property that when we take the quotient, they'll become line fields on the wall manifold. And the way that we build those quasi-invariant vector fields is using some special representations of Clifford algebras. So we have some complex Clifford algebra, and we look at this fancy complex spinor representation, and it is nice enough that it admits something that we're calling a quasi-real structure. And I don't want to get too much into the details, but we can use that to build the right number of quasi-invariant vector fields on this product space. And so they become line fields on the wall manifold. And you can read our paper and see the long, horrible formulas that we have for these vector fields. But I hope you can see the idea is very simple. You know, it's very, I don't know, very, very constructive proof. I'll quickly tell you about the upper bound. So that's the lower bound. We explicitly constructed some line fields on the wall manifold. And now we want to see that that's the maximum number that we can get. The upper bound is actually really, we're lucky that it's very simple. So what I want to show you is that the wall manifold fits into a nice fiber bundle. And the way you build this fiber bundle, we first look at this trivial one. So we have the product of the sphere with complex projective space. You can just project onto the first factor. And the fiber of this is CPN. So this is totally trivial fiber bundle. If you quotient out by this involution, so you have the antipodal action on the sphere and then complex conjugation on CPN, we get the Dold manifold as the total space, and the base is real projective space, and the fiber is still CPN. And then if you take mapping tori with respect to this, so you take the mapping torus of this fiber bundle with respect to the reflection in the sphere, we get this nice fiber bundle. So we have the wall manifold in the middle, the base space is the mapping torus of RPN, and then the fiber is still CPN. So anyway, it doesn't matter the details, but this is just a nice fiber bundle where the total space is the manifold we care about. And we just apply this lemma. It's a very easy to prove lemma. It's just kind of basic bundle theory. And let's just black box it for now. If you have a smooth fiber bundle, the fiber has to be sufficiently good. Then the projective span of the total space is bounded above by the stable projective span of the fiber plus the dimension of the base. Really easy thing to prove. And we just want to apply this to this fiber bundle where the wall manifold that we care about is the total space. This gives us our upper bound that we're looking for. So if we apply the lemma, it says that the projective span of the thing we care about is less than or equal to the stable projective span of CPN plus the dimension of the mapping torus of RPM. Now, just believe me, the dimension of this is m+1. And if you remember from long ago, if you have a simply connected manifold, there's no difference between the span and the projective span. So CPN is simply connected. So the stable projective span is the same as the stable span. And then there's this calculation of Steer, where he calculated the stable span of CPN. So we just basically immediately for free got the upper bound. And yeah, that's just the upper bound is very simple. And it was very weird for us because we didn't think of this upper bound till long before we found the lower bound. So we're like completely astonished when this worked out, because it seemed like such a random formula, but we should have thought of this the other way. You know, we should have figured this direction out first. That's the story of the projective span of wall manifolds. Now, in the rest of the time that I have, I just want to tell you about some related work. I hope I haven't bored you too much with wall manifolds. But fairly recently, I guess, my supervisor and Dermot Crowley revisited the proof of the Poincare-Hopf theorem for line fields. So we all know that if you have a smooth manifold, it admits a non-vanishing vector field if and only if the Euler characteristic vanishes. But it turns out that this is also true for line fields. So if you have a smooth manifold, it has a non-singular line field if and only if the Euler characteristic vanishes. And there were several proofs of this. Hopf himself proved it, but there was just lots of problems with the proof. So my supervisor and Dermot Crowley there was quite a lot of work in sort of fixing a few errors, but it turns out this is true. And the next step, the sort of idea of my PhD was to do the next obvious thing. So I was supposed to try and find necessary and sufficient conditions for projective span to be at least 2 or 3, say. And I spent the first half of my PhD or even longer trying to solve this problem, solving this problem for real manifolds. And then I learned that this was actually already known. So I just kind of reproved a bunch of things, and it's sad when that happens. But the good thing was in doing that, I learned all of this super high-tech, more Postnikov obstruction theory stuff. And so Nicola and I have recently solved the problem in the complex case. And so I just want to kind of tell you a little bit about this. So if you've got now a smooth manifold that's 2m dimensional, we want to now assume that it has an almost complex structure. And what that means is that the tangent bundle is isomorphic to the underlying real bundle of some complex vector bundle. This doesn't really, don't worry about this if you're a bit rusty with the bundle theory or whatever. It doesn't really matter. But this is an example result that we have. So say m is bigger than 2 and odd, then the complex projective span of this manifold is at least 2 if and only if you can find 2 line bundles over the manifold such that these virtual Chern classes vanish. So these virtual Chern classes, you can easily compute them in terms of the Chern classes of the bundles on the inside. So Cm-1 of this virtual bundle, you can write it in terms of the Chern classes of the tangent bundle of M and the Chern classes of these line bundles. So it's not, it looks more mysterious than it is, I guess is what I'm saying. And something kind of nice about these results is they're very specific. You know, they're not just saying, oh, there's the complex projective span is at least 2. If you know all the line bundles over your manifold, you can check using this result precisely which combinations of them will split off the tangent bundle and which ones won't. So it tells you a lot of information. We haven't completely written this up yet, but just in case you're interested, I'm showing you also the what happens when m is even. Unfortunately, it's not as nice, and there's some indeterminacy problems in the obstruction theory, and it turns out we don't know anything unless the top cohomology of the manifold is in the image of cupping with some characteristic classes. So this is kind of the downside of obstruction theory. Sometimes, you know, things don't totally work out, but it tells you precisely what you need to be true in order for it to work. But if the top cohomology of the manifold has these properties, then the penultimate Chern class is the total obstruction to splitting off the direct sum of 2 line bundles, 2 complex line bundles. Yeah, and we also have some results for splitting off 3 plane bundles or like direct sums of 3 line bundles, but it's a bit complicated, and I don't want to subject you to lots of boring technical statements of stuff. But we're writing this up, and I think it's going to be really nice. So I just wanted to advertise it. And I'm not talking about the methods that we used, but just for fun, I've drawn you a Postnikov tower. I really love drawing them. It's basically my favorite thing. I love these Postnikov towers. It's so satisfying to draw them. But this is, for example, like what you're looking at if you're trying to split off 3 line bundles. So here you've got the classifying map of the tangent bundle of this manifold with an almost complex structure. And we want to reduce the structure group. So we want to try and find a lift here. So here's this like leftover rank n-3 thing, and here's our 3 line bundles that we're trying to split off. And the fiber of this fibration is some kind of flag manifold. And the way these Postnikov towers work is you build somehow these spaces, and if it turns out if we can construct a map from M into this space E5, whatever it is, if you can manage that, then you can build a lift from here to here. And the K invariants that you compute tell you something about obstructions to building the map from M into E5. So this is how you can kind of get this obstruction theoretic information and solve your lifting problem. So anyway, I just wanted to show you this nice Postnikov tower. It's very fun, the computations, spectral sequences, and higher order cohomology operations, and lots of cool stuff. Also, if you ever need anyone to do any Postnikov calculations for you, I will happily do it. Okay, last thing I want to tell you, is another project that I have been working on. I'm really excited about, and it's much more close to being finished. I'm hoping it will be on the arXiv in a couple of weeks, really. It's sort of a hard fact that not every manifold is smooth. And so you can ask if there's some kind of notion of a vector field on a topological or a piecewise linear manifold. And the answer is basically yes, kind of. So cat is going to denote the category of smooth manifolds and smooth maps, or topological manifolds and continuous maps, or piecewise linear manifolds and piecewise linear maps. So you can have a closed connected m-dimensional cat manifold, and to such a manifold there is something called the cat tangent microbundle. So you get this, you don't get a tangent bundle, but you get a microbundle. It's a very weird thing. I will, well, I don't want to get into too long of a tangent. The thing is, these microbundles are horrible. Nobody wants to work with them, and they're very weird. But there are some very important papers that tell you that this tangent microbundle is isomorphic to a unique fiber bundle, which has fiber Euclidean space. And this is much better because it's more similar to like a tangent bundle that we know. And so I'm going to call it this tau m, and it's got kind of a funny structure group. And I shouldn't get too bogged down in the details of this, but anyway, you have some tangent microbundle for every cat manifold. You don't want to deal with it, so you look at the unique RM fiber bundle that's isomorphic to it, and this thing is classified by a map into this B cat M, whatever this cat thing is. And in 1975, Stern managed to define what a cat K field should be on a cat manifold. And I'm not going to tell you what the definition is, but I'll tell you what sorts of things happen if you have a cat K field. The main thing is that this cat tangent bundle will contain a rank K trivial cat subbundle. So this is what we kind of wanted. So if we had span at least K in the smooth case, then we knew the tangent bundle had a rank K trivial subbundle. And that's what we're getting here. So we have a cat K field, and somehow this cat tangent bundle also has some sort of cat trivial subbundle. But the problem is, just to be truthful, linear independence doesn't make sense anymore in this context somehow. So you can't, the problem of splitting off a subbundle is no longer the same thing as containing a subbundle. So there's some kind of weird difference there. But anyway, the big theorem that we have that I'm very excited about is we have some manifolds is a cat manifold, it's oriented, and its dimension is 0 mod 4. Then we can prove that the cat span is at least 2 if and only if the Euler characteristic vanishes and the signature vanishes mod 4. And this proof was well known, or this result was well known in the smooth case from long ago. But the problem is the proofs in the smooth case depend on the Hirzebruch signature theorem and also the Atiyah-Singer index theorem. These things do not work for topological and piecewise linear manifolds. So the proofs couldn't be generalized, but we've given a totally obstruction theoretic proof. And then it's not easy, but you can kind of circumvent the mystery of the cohomology of B cat and lift this argument to work in these other categories. So I wanted to advertise this. I'm hoping it'll be on the arXiv soon. But yeah, this is all I wanted to say. Thank you so much for listening to all of this. It's really nice to share what I've been doing. Thanks very much.
It's thank you, Baylee, for a wonderful talk. Does anyone have any questions for the speaker?
Hi, so the last theorem you mentioned, classically in the smooth case, like what's the theorem called?
The theorem in the smooth case. Well, it's not really called anything, but
Or who is
it's
it by? Yes.
yeah, it's usually attributed to Mayer, but it was also proven by Frank and also Attia. So I can send you some papers if you want to read the. If you the easiest place to look though is just Frank. I think his paper is called The Index of Two Fields on Orientable Manifolds or something like that. So that's
Yeah, all right.
probably
Thanks. That's really good one.
sure.
So before I stop the recording, are there any other questions that people want to ask that they don't mind being on the video?
Yeah, so I'm a bit curious about the like why the p-span of them, like the difference for m being odd and even, like where does that come into play?
Oh yeah.
I feel like the thing I would assume to be the pretty case seems to be the ugly case, and that's
Oh yeah. Okay, sorry, let me go back. Oh, whoops, I'm on my turn. I know what you're talking about. That is true. So this what you're saying, the odd and even here?
yes, I would want it to be pretty when m is even, not odd, intuitively.
Yeah, I guess that is kind of weird. The reason, maybe I can just, this isn't the right Postnikov tower, but I can kind of show you the reason why. So the way that these K invariants show up, the different obstructions, you see that there's all these Eilenberg-MacLane spaces of some type, and the group that shows up in these Eilenberg-MacLane spaces is a homotopy group of the original fiber that you start with. And in these cases, I've got, yeah, some flag manifold is the fiber, slightly different from this one. And when M is even and when M is odd, the homotopy groups of it are different. And it just turns out that they are worse somehow in the M is even case. And it just makes the obstruction theory much more complicated. But that's basically the reason.
Okay, that makes sense. Thank you.
Thanks. Sorry.
So maybe I'll stop the recording.